Quantum computers leverage quantum bits, or qubits, which can exist in multiple states simultaneously, unlike classical bits. This allows them to solve complex problems exponentially faster. Key applications include cryptography, optimization, and drug discovery, revolutionizing industries by providing unprecedented computational power. The quantum internet represents a revolutionary shift in connectivity, utilizing qubits and quantum mechanics to enable unprecedented data exchange. It promises advanced cryptography, long-distance entanglement, and distributed quantum computing. Unlike classical networks, it leverages superposed states for enhanced security and efficiency, marking a new era in communication technology. The quantum internet is a revolutionary network enabling quantum devices to exchange information using quantum mechanics. It leverages qubits, allowing data in superposed states, unlike classical bits. This promises advanced cryptography, long-distance entanglement, and distributed quantum computing, offering capabilities beyond the classical internet. Currently, it's in early development stages. Qubits, the core of quantum computing, differ from classical bits by existing in superposition, embodying both 0 and 1 states simultaneously. They are represented by true two-level systems, like photon polarization, or pseudo-two-level systems, such as atomic energy levels. Their state is a vector in a two-dimensional complex space, with probabilities summing to 1. Qubits, the fundamental unit of quantum information, differ from classical bits by existing in superpositions of states. This allows them to represent both 0 and 1 simultaneously. Qubits are realized through systems like photon polarization or electron spin, and their state is a vector in a two-dimensional complex space, with probabilities summing to 1. Superposition enables qubits to exist in multiple states simultaneously, allowing quantum computers to process numerous possibilities at once. This capability is crucial for tackling complex problems beyond classical computing. Quantum interference, arising from superposition, can bias qubit measurements toward specific states, enhancing computational efficiency and precision. Quantum entanglement links the states of particles, even when separated by vast distances. This correlation allows for stronger than classical coordination. Measuring one particle's state instantly influences its entangled partner. Entanglement's exclusivity enhances security, crucial for encryption key generation. Entangled photon pairs are a practical source for diverse applications, leveraging this unique quantum property. Quantum teleportation enables the transfer of a quantum state between distant particles without moving matter. It requires a pre-shared entangled state and classical communication. Alice measures her qubit with a bell pair, sending the result to Bob. Bob then applies a specific operation to his bell pair half, reconstructing the original quantum state. A bell pair is essential in quantum teleportation, consuming one pair and requiring 2 classical bits for measurement. It respects the no-cloning theorem. The original qubit is destroyed, leaving only the target qubit. Teleportation doesn't allow faster-than-light communication, as classical channels limit speed. The circuit diagram illustrates this process, highlighting the roles of qubits and classical bits. Quantum key distribution, QKD, leverages quantum mechanics to ensure secure communication by detecting eavesdroppers. It generates shared, secret random numbers as cryptographic keys. The security hinges on the principle that measuring a quantum system disturbs it, revealing any eavesdropping attempts. If anomalies exceed a threshold, key generation is aborted, ensuring security. Arthur Eckert's E91 protocol uses entangled photon pairs, ensuring secure communication by detecting eavesdropping through destroyed correlations. The BB84 protocol, widely implemented, uses single qubit preparations and measurements. Quantum key distribution systems are commercially available, integrated into encryption suites, and tested in cities like Boston and Vienna. Trusted repeater networks are foundational for a quantum internet. Quantum signals face significant challenges due to their fragility and susceptibility to environmental perturbations. Decoherence causes qubits to lose quantum properties over time. In fiber optic cables, qubits are prone to loss and dispersion, leading to errors. Absorption losses and depolarization errors increase exponentially with distance, limiting current experiments to several hundred kilometers. The no-cloning theorem asserts that exact copies of unknown quantum states cannot be made, impacting quantum networks by preventing signal amplification without destruction. Classical error recovery methods relying on cloning are inapplicable. The no-broadcasting theorem further restricts quantum information from being sent to multiple destinations simultaneously, unlike classical networks. These principles ensure eavesdropping attempts disturb quantum states, enabling detection. Quantum repeaters are crucial for long-distance quantum communication, overcoming the challenge that quantum signals can't be amplified without destruction. They establish entanglement between distant nodes by dividing long links into smaller segments, creating entanglement across these, and then stitching them together through entanglement swapping, ensuring efficient quantum information transmission. Quantum repeaters perform three operations: entanglement distribution, purification, and swapping. First-generation repeaters use heralded entanglement and purification. Second generation introduces quantum encoding and classical error correction. Third generation employs quantum encoding for deterministic correction, enhancing entanglement distribution rates by removing two-way classical signaling. These advancements improve the efficiency and reliability of quantum communication networks. Quantum networks mirror classical networks with nodes, links, and layered architecture. The application layer interfaces with users, while the transport layer ensures reliable transmission. The network layer manages routing for entanglement, and the quantum link layer handles entanglement resources. The physical layer connects nodes for qubit transmission. Nodes include entanglement sources, memories, detectors, and repeaters, with classical channels for control information exchange. Quantum memories are crucial for global-scale quantum internet and high-performance networking. They must store and release qubit strings on demand, with performance measured by fidelity, efficiency, and storage time. Approaches include optical delay lines, electromagnetically induced transparency with atoms, photon echo in solids, nano-optomechanical systems, and atomic frequency combs. Despite progress, development continues for practical implementation. Integrated photonic platforms are pivotal for quantum internet technologies, enabling miniaturization to chip level for cost and energy efficiency. Silicon-based waveguide architectures are leading, leveraging complementary metal oxide semiconductor technology. Other platforms like lithium niobate and nitrogen vacancy centers in diamond are emerging. Challenges include integrating fast feed-forward and quantum memories, with new techniques anticipated. China has established the world's longest quantum key network from Beijing to Shanghai, with plans for a 35,000-kilometer national network. The MOSI satellite, launched in 2016, demonstrated quantum communication over 1,203 kilometers. China claims quantum advantage with the Zhuzhong prototype, performing calculations 180 million times faster than supercomputers, and achieved high-speed quantum teleportation at 7.1 qubits per second. The United States is advancing quantum internet through initiatives like the Department of Energy's Research Blueprint and a 129-kilometer quantum network near Chicago. Key players include International Business Machines, Google, and Defense Advanced Research Projects Agency. National Aeronautics and Space Administration explores global quantum communication via the International Space Station. Europe plans a secure pan-European network, while Switzerland's Swiss Quantum Initiative and projects like National Center of Competence in Research SPIN drive innovation in quantum computing and cryptography. The quantum internet promises transformative applications beyond classical capabilities. Secure access to remote quantum computers enables blind quantum computing. Distributed quantum computing connects distant quantum systems for complex tasks. Enhanced sensing and imaging leverage entangled particles for superior precision. Long-distance entanglement improves clock synchronization. quantum cloud computing and distributed storage offer secure data management, while scientific collaboration benefits from real-time remote device access. The quantum internet, an emerging field, promises to revolutionize communication and computing. Governed by quantum mechanics, it demands a shift from classical networks. Global efforts are advancing, yet challenges remain in hardware, processing, and secure connectivity. Collaboration across disciplines is crucial to harness its full potential, transforming cryptography and ensuring secure, long-distance quantum connections. Thank you for your attention.